So last time we discussed about what is a region and then what are the typical regions that a compiler constructs. Now we're going to talk about how we can construct a region hierarchy. What is the algorithm to construct such a hierarchy? Assuming we already know what regions we want to compute, how would the compiler go about actually creating such a region hierarchy? And in this discussion, as as we have been doing in the past modules as well, we'll assume that the CFG, the control flow graph, is reducible. And the rationale for that is that most programs produce reducible graphs. And even if there's an odd program or an odd part of a program that is not reducible, it is possible to convert it to a reducible graph using code duplication. Even though that can potentially cause increase in code size, hopefully such cases are going to be rare, and so it becomes a practical solution. All right, so our regions, the choice of regions for our compiler is going to be the same as we had discussed in the previous module. It's going to be basic blocks, and these are going to form our leaf regions. So notice that I'm not using regions for modeling individual instructions. My lowest level regions are going to be basic blocks, and this is on purpose because it just makes you can just summarize the transfer functions of basic blocks, and then based on that you can do the DFA, and that just improves the efficiency of your algorithm. It doesn't make any difference to the precision, but it improves the efficiency of the algorithm. Sometimes it may actually also make the improvement to the precision if you are able to identify a more precise transfer function for the basic block than simply the composition of the individual transfer functions of the constituent instructions. In any case, I'm going to assume that the leaf regions are going to be basic blocks. And then there will be a hierarchy of regions which will be based on the loop hierarchy. So natural loops would form the next levels of regions, and this is again I'm considering bottom to top of my region hierarchy. So natural loops, in other words, would be inside out. So I'm going to first construct the innermost loops, then the outer loop, then the outer loop, and so on until I reach the outermost loop. And also each natural loop will define two regions actually. So for every loop, even if it's the innermost loop, there will be two regions that loop would define. One would be the region corresponding to the body of the loop body, which is the acyclic graph of its subregions, and then the loop itself, which is made up of one subregion made up of this loop body, and then the back edge. Recall that the region formed by the loop body is basically nothing but the region formed by the loop without the back edge, and so conversely the region formed by the loop is nothing but the region formed by the loop body plus the back edge. And finally the top level regions are going to be the procedure bodies. Alright, so here is an example. Let's say I have this program and I equals 0, if I is less than n then you exit, and then inside the loop there is some branch on some other variable x. If x is greater than 0 then I plus equals x, otherwise I minus equals x. Alright, so in this, if I was to create a loop hierarchy, I'm going to show what the loop hierarchy is going to look like, and this time I'm going to show the loop hierarchy top to bottom. Alright, although we are going to construct it bottom to top as we discussed in the previous slide, I'm going to show this example, the result of that algorithm, and the result I'm going to show as a top to bottom exposition of the hierarchy. So recall that the top level region for this is going to be the procedure region, and that procedure region's subgraph is going to be made up of two subregions. One is going to be B1, which is going to be just the basic block, and the second is going to be the loop region that's going to represent this entire loop. And then the loop region's outgoing edge is going to go to the exit node, just like in the original CFG, control flow graph. So this represents the top level graph as the DFA analysis would see it, right? For the procedure, it's just a graph made up of two nodes, all right? Of which one node is, it's at this level, I don't even know what these nodes are. But when I go one level deeper into the hierarchy, I will find out that this node is actually a basic block and the second node is actually a loop, and so I would have I can basically do more inside those loops. But when I'm going to run the DFA at this level, it just looks like two different nodes, and I'm just going to assume that I have summary transfer functions for both these nodes. Now similarly, I can go to the next level, and for the basic block, I'm already at the leaf node. For B1, I'm already at the leaf node. But for the loop region, I would have the next level of the hierarchy. And so this is the hierarchy. This is the graph that would be, this is what the graph for a loop region would look like. And this is actually true for any loop, because for any loop, recall that we are basically constructing two regions. One is for the loop itself and one is for the loop body. And so we're just going to abstract the whole loop body as a single node and then have a back edge to it, and then have an entry and an exit. And so this is the graph that is generated at the next level of the loop region. And so the DFA is going to run on this this abstracted version with just one node and a back edge and an entry and an exit edge. And I should have a summary transfer function for the loop body region. And based on the summary transfer function of the loop body region, I may want to construct a summary transfer function of the loop region. Recall that the fallback summary transfer function of the loop region would just be the result of running a fixed point DFA iteration on the summary transfer function of the loop body region. But maybe you can do better using symbolic analysis, as we had seen previously. Now this is the second level of the region hierarchy. It only has one node, but this node actually, when I dig deeper, if I go one level down the hierarchy, I would find that this is actually it has a control flow graph. It's not just a simple basic block, right? And so this is what the loop body region would look like. It would have B2. So this particular node I'm calling B2. It's labeled B2. B2, B3, B4, B5, B6. So the control flow graph for the next level of hierarchy is going to be the entire loop body. And this is going to be the entry, and it's going to have two exits this time. Notice that one exit is actually going to the program exit. So one exit of the region is going to go to the exit of the program. And the other exit of the region is actually not going to go to the exit of the program, but it is going to go to the back edge. And recall that in the loop body region, I'm not including the back edge. And so the outgoing edge just looks like a region exit. And so in this particular loop body, it seems like, and also we basically have two exits for this particular loop body region. One for the program exit itself, the original exit, and one for the loop back edge, because the loop back edge is not captured at this level of the loop body region hierarchy. Now, at this point, at this level of the hierarchy, all the subregions B2, B3, B4, B5, B6, notice that all these correspond to these, also been labeled in the original control flow graph. All these correspond to the leaf regions because they are all basic blocks, and so I'm not going to there's not going to be an other level of hierarchy, and we are already at the bottommost level of the hierarchy. Finally, what are the basic block regions going to look like? Well, for every basic block, including B1, which I had shown in the first slide of the top level region, the procedure region, every basic block would have a region which is just going to be made up of single node and two edges, one coming from entry and the other coming from exit, right? Sometimes it can have two outgoing nodes, but because it's a single node, it doesn't matter. I can it just looks like it's a single exit from that particular basic block. It can also have two exits, in which case the transfer function should summarize. There should be two transfer functions for each of the exits. So there would be one transfer function of B2 that goes from entry to first exit, and then there would be a second transfer function for B2 that's going to go from entry to the second exit. Some of the basic blocks have only a single exit. Some of the basic blocks have more than one exit. It could be 2, 3, 4, whatever. If there are more exits, then there should need to be separate summary transfer functions for each of those exits. But the common thing about all these regions is that they all have a single entry, and recall that that's just by the definition of a region, including the regions formed by basic blocks, the region formed by loop bodies, the region formed by loops themselves, or the regions formed by procedures. All these basically need to have a single entry. They can potentially have multiple exits. Alright, so how am I going to construct the region hierarchy? I just showed you what is the expected result of the algorithm on a given example, and we looked at all the levels of the region hierarchy. But then what is the algorithm to construct this solution? And we're going to construct the region hierarchy bottom up. We are going to first identify all the basic blocks as regions, and we know how to identify basic blocks. We've already discussed how a control flow graph can be split into basic blocks, and you identify all the straight line sequences of instructions which can only jump to the beginning of that sequence of instructions, right? So that you basically, and then you replace them with a single node, and you record this relationship between the node and the constituent sequence of instructions, right? So that forms one level of my region hierarchy. Notice that we are using a bottom-up strategy to construct the region hierarchy, and that's why we start with first constructing the regions associated with the basic blocks. Then the next level is basically we need to identify the natural loops from the inside out. So we already have discussed how to identify natural loops. We identify back edges, then we identify the header of the loop, and based on that we identify all the nodes in the loop. Now once we have identified all the loops, we also construct a hierarchy of the loops, and we also discussed how we can call one loop to be nested within another loop. If the header is part of the loop, if the headers are disjoint, then if all the nodes in one loop are a subset of all the nodes in the other loop, then we say that the first loop is nested within the second loop. And so we identify the natural loops and their hierarchy based on that algorithm, and then we use that to construct our regions. And basically we are going to do what the expected thing. We are going to replace a loop L with a node in two steps. First, we are going to construct a region for the body of the loop, and we know how we have already identified the body of the loop using our loop identification algorithm, which is all the nodes and edges except the back edges to the header, right? And this body of the loop is replaced by a node representing region R. Okay, and edges coming into the loop header now come into R, and edges going out of the loop now go out of R. So when we are actually collapsing a region into a single node, we have to also worry about what are the edges that are going to come into this node and what are the edges that are going to go out of the node. For example, when we talked about constructing a region out of a basic block, what are the edges that are going to come into the node? These are all the edges that would have come into the header of the basic block. What are the edges that will go out of a basic block region? These are all the edges that go out of the last instruction of the basic block, and they could be either one outgoing edge or could be two outgoing edges, depending on whether it's a conditional branch or an unconditional branch or a fall through. Similarly, for a loop, all the incoming edges to the single node R for the loop body is going to be all the edges that are coming into the header of this loop, except the back edges. All right, so we're not going to consider the back edges at this stage because we are only interested in the body and not in the entire loop. Similarly, what are the loop edges going out of this particular node? These are all the loop exit edges. Loop exit edges are edges that have the source node belonging to the loop and the destination node not belonging to the loop. All right, and so all such edges are the outgoing out of the loop are now going to go out of R. And we have already talked about if there are multiple edges that are going out of a region node, then when I'm constructing summary transfer functions, then I need to have different summary transfer functions for each of those exits from the entry. All right, and finally, so these back edges would become self loop edges on R. So now at the next level of hierarchy, I'm going to actually identify the loop itself as a region. And when I'm going to do that, all the back edges would now become self loop edges on the R. And in fact, they can be, they can be either collapsed into a single edge, or they can be retained as different edges, depending on what is the type of symbolic analysis you are interested in doing for that particular level of the hierarchy. All right, and R is called a body region. We have already discussed that because R is formed out of a body. And then this is what my higher level region looks like. So this body region becomes a loop, and this higher level region now becomes a loop region. Okay. Now I want to again kind of discuss what happens if the body has two back edges. So two back edges going into the header of the loop, in which case we would have two edges, maybe something like this, and two back edges at this level of the hierarchy for the same node. And we may want to retain this information because our symbolic analysis may rely on this information to be able to compute more precise transfer functions for the entire loop. So notice that at every level of the hierarchy, based on the summary transfer functions of the subregions, we are computing the summary transfer functions of the current region. So for example, in this case, based on the summary transfer function of the loop body, we are going to compute the summary transfer function of the entire loop. And we can do this either using a symbolic analysis, or our fallback implementation can just be to just run a fixed point iteration, and whatever is the answer, we basically give that as a summary transfer function of the entire loop. So once again, first the loop body of the L is constructed and is collapsed into a region R, and second, a region R prime that includes R and its self loop is constructed. So that becomes the next level of hierarchy, which includes the back edges, and I'm calling that particular region R prime. So there are two regions that have been created, one nested in the other, R for the body, R prime for the loop, which includes the body, which includes R and its back edges. So in our particular example, if this was my control flow graph, then and all these circles in the original control flow graph represent basic blocks. Then after doing the first level of loop body regions, I'm going to get a graph like this, where R represents the loop body, and the back edge still is available in the loop, in the control flow graph. And after doing the next level of region hierarchy, I'm going to get rid of the back edge, and this is going to be my loop region R prime. Eventually, all natural loops would get collapsed into single nodes. Recall that we are only discussing reducible graphs, so all cycles are loops, and so we already have algorithms to reduce or collapse all loops into single nodes. And so at the very end, we are going to be left with a directed acyclic graph for the procedure body. So what we are going to be left with is a directed acyclic graph, and we can see that even in this particular example, we are left with just 2 nodes and 3 edges, and this is a directed acyclic graph, or DAG. And so we are going to be left with a DAG for the procedure body, and this DAG can be collapsed into a single top level procedure region. And so we have finished our procedure for constructing the region hierarchy in this way. So notice that we constructed the regions in a bottom-up fashion, first constructing basic block regions, then constructing inner loop regions, then inner loop region bodies, then inner loop regions, then outer loop bodies, outer loop regions, until I get to the top level, outermost loop body, and then outermost loop region, and finally the procedure region. And this will form my region hierarchy tree.